This talk comes from my turbulent experimental past. The reason I'm giving it is the phenomenon in question, CIDNP, chemically induced dynamic nuclear polarization, has, after a fashion, come back from the dead on the back of the DNP bandwagon, because it happens to share the three letters DNP. And also it produces extra polarization compared to the Boltzmann level. And seeing as DNP is so popular at the moment with the community, CIDNP, ironically because it's something completely different, has been given, has been recovered from the dustbin of history. This dates back to 2007 and to the University of Oxford. Now, what is CIDNP? The reason for the acronym is a historical mistake. When people first discovered it, they saw extra polarization in systems that involve radicals, and so the natural thing to ascribe it to was to the overhauser effect, which was discovered not very long before this CIDNP effect appeared. After a few decades of thinking, another mechanism emerged as something that is actually causing it, and here is the summary of that mechanism. Now, where it starts from is a molecule called a photosensitizer. It is usually a coenzyme or something that is closely similar to one that we need to photoexcite, and for that we need a laser, and the ground state of that molecule will absorb a quantum of usually blue or green light and go into its singlet excited state. Now, as we know, excited states, because they've got various couplings, spin couplings inside them, can undergo what's called intersystem crossing, and the two electrons which were initially anti-parallel at the point of excitation become parallel, cross over into the triplet state, which for some molecules, and this isn't for every molecule out there, you have to specifically look for them, this is very electronegative. That is, it has a huge energy of electron abstraction. If we happen to have an electron donor nearby, what would happen is this electronegative triplet state will grab an electron for itself, thus creating a radical pair. Now, chemical reactions of that kind are spin conserving, and so the original triplet state of the photosensitizer becomes the triplet state of a radical pair. We have a hole on the donor molecule and the electron on the acceptor molecule, but the hole and the electron are still correlated into the two-particle triplet. Now, the fate of such a radical pair depends on the subsequent dynamics in the two electron subspace. As you know, radical pairs that encounter each other in a singlet state are likely to recombine. Yeah? You need a singlet to form a chemical bond, and radical pairs in a triplet state will not recombine and are likely to drift apart. So, depending on the fate of this triplet state, we can either have a separation into two doublets, or we can have a recombination eventually back to the original electrically neutral states. But the singlet-triplet mixing in the two electron subspace is a magnetic phenomenon, and it is modulated by various magnetic interactions inside those radicals, most notably by the hyperfine interaction. And so you see what happens. The chemical fate of the reaction starts to depend, although very indirectly, on the nuclear magnetic interactions inside the molecule. And it so happens that the reaction starts sorting. Very simply speaking, spin up from spin down in the nuclear submanifold. This separation, because the paramagnetic relaxation is extremely fast, generally doesn't produce any nuclear polarization, because by the time they have hit a wall or recombined with something else, the nuclei have relaxed because of the paramagnetic interactions to the electron. However, this pair recombines fairly quickly, and so we have, in a way, a chemical reaction which proceeds in a way that is selective with respect to the nuclear configuration in the molecule. And so it sorts some nuclear states which go into the products, and other nuclear states which stay in the unreacted species. I have an animation here as to what's actually happening. There flies our photon, so we have an optical excitation of the photosensitizer. Boom, it gets photoexcited. Then there's electron transfer from the donor molecule and nuclear spin selective evolution inside the resulting radical pair. Then we've got recombination, but it only happens for some nuclear configurations but not others. And then eventually there is separation and backwards electron transfer, and we have a molecule but with polarized nuclear states. And then there can be an induced emission of a radio frequency quantum, which then flies into our detector, and we see the enhancement of our signal. So this is what it basically looks in practice. You have some enhanced signals in the result. This is what one can reasonably expect. On protons, we typically get about a factor of 10 relative to Boltzmann level. On fluorine, because of the huge hyperfine interactions on the fluorine nucleus, about a factor of 40. And then there are bigger hyperfines, but also smaller magnetogyric ratios for the carbon-13 and nitrogen-15. So at most, on a very good day, in a really well-tuned system and a really monstrous laser, you can get these factors. Typical things on a bad day with an average laser is about a factor of 10 less. Now, theory of the process has been developed in fine detail. You can go very deeply into it. You can actually consider specific spatial diffusion of those radicals around each other, and they're held together by the solvent cage and held together by the Coulomb interactions. And it is very complicated dynamics. But empirically, once everything has subsided, CIDNP can be treated as just a source term for the magnetization. So if we've got d by dt of, for example, the longitudinal states, and on fluorine we actually had to include the cross-correlation processes as well, because CSA on fluorine is quite huge. We have relaxation rates, we have cross-relaxation and cross-correlation rates, and there will be the pumping terms, just the extra source terms to the Liouville-van Neumann equation, which replenish the population difference on some spins as the process goes. And that's the sort of picture that you get on a really good day. That is the Boltzmann level polarization on the fluorine nucleus and fluorotyrosine, and this is what you get after burning it with a 5-watt laser for about 6 seconds. So basically what we have is optical pumping with a laser, which feeds into a cyclic magnetosensitive reaction chain, and after something really complicated happens inside the magnetosensitive reaction chain, we get nuclear magnetization. Importantly, because the reactions involved are to a very large extent cyclic, there is no overall chemical reaction taking place in the sample. That is, after that laser flash has happened and all the chemistry has taken place, you get your system back, but in a nuclear spin polarized state, which is a significant advantage. Over, for example, parahydrogenation, that is, you're not actually chemically modifying your system except in a transient short-lived way. So the basic summary of where it comes from is radical recombination probability modulation by nuclear hyperfine interactions. You can see this is something completely different from the mechanism of the actual real DNP. And well, the reactions in question can only happen if the donor molecule is physically accessible to the photosensitizer. That is, if it is an amino acid and there are 3 amino acids which are readily polarizable in a protein, tyrosine, tryptophan, and histidine, because they're aromatic and electron can actually be torn away from them at a reasonable cost, the amino acid residue has to be positioned on the surface. And so if we have a protein and we perform a CIDNP experiment on it, what would happen is the surface residues will get polarized and the signals will go up, but the residues which are buried in the protein core will not get polarized. And so this is a method that would allow one to selectively study the protein surface as opposed to the protein bulk. And in particular, because surface is modified by folding processes, one can gain information about what became solvent exposed during the protein folding process. Then there's chemically pumped NMR. Of course, you can do various things to extra polarization that you've generated. And one other important thing is the resulting magnetization carries an imprint of the hyperfine couplings that were there in the original radical. And also of the G tensor of the kinetic parameters. Those can be extracted by fitting. And so we can get some information about structures of possibly very short-lived radicals and various kinetics rates in there from analyzing the cidNP dynamics. But well, before we proceed to analyze cidNP dynamics, there's a small matter of building the stuff. You've got to get the light into the sample, that is, into the NMR spectrometer, into the core region of the magnet, and there are various ways of doing it. Well, there are two light sources to start with. There are continuous wave sources, just like this laser pointer. It just shines continuously, although at much greater power. And there are pulsed sources, which give microsecond or even nanosecond long light pulses. Now, it's very easy with continuous wave sources. What one simply needs to do is focus the laser into an optical fiber, bring the fiber into the magnet, and what people usually do, this is called the Berliner setup, is to use the standard coaxial insert, which is used for external reference. In, for example, phosphorus spectroscopy, this is where you would put the phosphoric acid rather than your sample, to use it as a reference, and so it can just house the fiber. It's a bit of a shimming challenge, but not too much of a problem. And sometimes the sample needs to be refreshed, because certain amino acids do tend to get burnt out and oxidized. And so this is how the system looks, and it's been perfected rather well over the years. Alternatively, if the sample is optically dense, and we'll get back to that point in a moment, you'd want to bring the light a little bit closer to the actual coil region of the sample. But more on that in the next couple of slides. And pulsed sources are, as we shall see, extremely difficult. Now, we need to bring a few millijoules of light energy into the sample, and the duration of that pulse is typically in the nanoseconds, and you divide millijoule by a nanosecond, you get a megawatt. Yeah, it is very considerable energy density, and fibers are not an option simply because a fiber is exploded if you try focus that sort of light intensity into it. And then you've got to make sure that your fiber can actually handle that. And in our case, we just focused our 25 volts into the fiber, and well, nothing happens. It actually becomes really hot, but it can transmit continuous wave. It certainly cannot transmit the pulsed sources, and I will not show you the exploded fibers. Now, this is something that comes necessary with optically dense samples. We had to study things like GFP, green fluorescent protein, which is unfortunately green and fluorescent, so it eats all our light and fluoresces it on the yellow wavelengths, which doesn't excite the photosensitizer. So, and otherwise, if we just, shine light from the top here, it will get absorbed in the first millimeter of the sample, and nothing will reach the coil region. So, a little bit of thinking came up with a procedure where an optical fiber is squeezed step by step into hydrofluoric acid. And you can see why it didn't sit particularly well with either my supervisor at the time, Peter Hoare, or the safety officer, because we proposed to put the fiber into boiling hydrofluoric acid, which is a terrible toxin, blah, 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 blah. And so I had to do it on a Saturday night, then take these pictures, leave them on Peter's table on Monday morning, and not turn up on Tuesday. And then on Wednesday, knocking on the door, seeing very angry Peter telling me to publish. And it went without revisions into JMR. So it sort of scatters light sidewards, and because most of the susceptibility discontinuities here are parallel to the direction of the magnetic field, it's actually fairly easy to shim. And it doesn't particularly destroy the resolution. Certainly the heating that the light causes anyway is a much bigger problem resolution-wise than any external optical fiber tubes like that. That's an illustration. If you shine light from the top, here you get Beer-Lambert's law. Light decays exponentially in the sample, but if you irradiate it with an optical fiber shaped like that, it sort of uniforms through the the length of the sample. This is one other use of photo-CIDNP effect, which I haven't really used myself or have seen used anywhere. In the linear regime, under small light intensities, the nuclear polarization that the CIDNP causes is proportional to the local light intensity. That is, if you have some light intensity distribution within your sample, you can actually measure it by recording, imprinting it in the magnetization, and then doing magnetic resonance imaging on the result. Might be useful in optics somewhere. But in principle, this allows you to map light intensity distributions by MRI, because it connects the local light intensity directly to the magnetization. Now to the pulsed setups. If we have a pulsed laser, then 100 millijoules in 8 nanoseconds is 12.5 megawatts, and this is what happens to a fused silica lens if you are not careful about cleaning it properly or focusing your light inside the volume of the lens rather than outside of it somewhere. So what had to be done is we had to avoid focusing the light into a point at any time, because if you focus it in the air, the electric field in the electromagnetic field of the light is so strong it strips electrons of nitrogen, so you get a blue spot in the air. So there had to be a very, very long focal length lens which doesn't focus the light to a point even there inside the magnet. And then the sample is capped not by a fiber but by a fused silica rod, which goes all the way to the coil region. Unfortunately, it has to be illuminated from the top, or alternatively from the bottom, but in that case we'd have to drill the probe. And so there was the laser. This prism was standing on the table. That prism was bolted to the ceiling, and this prism was bolted to the ceiling right above the magnet. Here it is, and there are sort of X, Y, Z, theta, blah, blah, blah controls that direct the beam into the magnet, and the probe had to be taken out, and there was a target on the floor. You hit the target first, and you put the probe back in, and you get it going. Now again, safety officer had a problem with it, because if 12.5 megawatt bounces off any of these shiny surfaces, is a bit of a problem. So when this was discovered by Keith McLaughlin, who just trundled into the office one day, I was banned from using this equipment for a month, and thereafter until I enclosed the beam. And well, thankfully enough data was collected by the time, so we didn't actually have to do it. We just dismantled the whole thing and wrote up the papers. But yeah, we gained a bit of notoriety with the University Safety Office. But well, the good thing is this was working, and it was even compatible with cryo probes, because the illumination is from the top, and you don't need to drill anything or stick any sort of fiber into the place where liquid helium would have been. That's a schematic of it that went into Rep Scientific Instruments. We actually need 3 TTL lines from the back of the barium. One controls the flash lamp on the neodymium YAG rod, the other the Q switch, which is what triggers the laser. And then there's a safety interlock shutter, which even I had to put in, because otherwise I would have been blind now. There's a photodiode at the target, which will actually tune the magnet geometry. Remember, the magnet is suspended in air, and that geometry is sufficient, reproducible for a couple of hours, so you can still hit it, but you've got to retune it every time you do the experiment. Into the attenuator, into the oscilloscope, as you'd have to do with barium, because at that time you couldn't trust the console as to what it actually outputs into the coils, and well, then the workstation. So relatively easy to install any spectrometer. You need a bunch of mirrors, a laser, and a quartz rod that is transparent to the UV lights as the laser outputs. Okay, so well, you've built the system. What can you do with it? Well, it pumps magnetization. It pumps huge levels of it, and the obvious thing to do with it is nuclear overhauser effect. And for the students present, nuclear overhauser effect is something that occurs due to the presence of these transitions. This vertical one, when 2 spins are flipped at the same time, and this one, when they're also both of them flipped at the same time. So technically speaking, such transitions are forbidden in coherent dynamics. Their probability is extremely low, but they're actually allowed in second-order time-dependent perturbation theory through the various relaxation mechanisms, dipolar in particular. And so what this means in practice is the magnetization can drift from one spin to nearby spins. And if we've got extra population difference on a particular spin, it will find its way around the system. And so we can transfer it around and maybe polarize some other spins. And what was interesting, we could polarize significant, well, inaccessible otherwise, levels of multi-spin orders as well. So you can pump the two-spin order to about 2 times what it would have been otherwise if you were to do it from Boltzmann levels. And if you just give it a pulse and let it relax, then it grows and relaxes as it should, and it all fits correctly. And then, of course, in bigger spin systems, you've got more complicated transitions. You've got double quantum, triple quantum, and so on. And it rapidly gets very complicated. But it can still be analyzed, and it obeys all the expected dynamics. So if you take that system and record the dynamics of every spin order, you can realistically measure, and then fit the standard Redfield theory to it with the standard coefficients that depend on the correlation time and the molecular geometry. Then, as you can see, the fit is pretty good. So, for practical purposes, the continuous wave cidnp radiation is just extra magnetization source that continues pumping your system to negative temperatures. What's necessary in practice? What kind of things get polarized? They have to be aromatic. That is, the ionization potential has to be low enough for the photosensitizer to actually be able to tear away that electron to kickstart that entire process. If it's alanine, it's aliphatic, the ionization potential is somewhere in the ultraviolet, and cidnp wouldn't happen. So in practice, tryptophan, tyrosine, tryptophan, and histidine. I was working specifically on fluorinated ones because hyperfine couplings on fluorine tend to be huge, and relaxation behavior is also quite interesting. And so all these aromatic things are simply fluorinated in various positions just to make sure that the hyperfine coupling is strong enough. So needs a low ionization potential, needs a hyperfine coupling on the nucleus of interest, needs to actually react with the photosensitizer, needs to be sufficiently soluble. You need of the order of 4 millimolar concentration of that thing before the phenomenon becomes useful, and the important matter of geometric accessibility. If the photosensitizer cannot approach the aromatic system, then the reaction wouldn't happen for simple geometry reasons. This is what you see when you do the experiments. This tiny little bump thing is the dark, that is just the usual NMR spectrum. And then you start shining laser on it, and it grows and eventually loses the shape because of the non-uniform sample heating. When we've got a 5, or in the later days 25 watt laser, you have to be pretty careful so as actually not to boil your sample. So 6.4 seconds at 5 watts is what, 30 joules. That is about 8 calories, and a calorie is what it takes to heat 1 gram of water by 1 degree. So we were having temperature gradients of the order of 10 degrees in the sample by the end of this illumination, hence the drop in the line width. cidnp effect can be negative as well as positive. It depends on the sign of hyperfine coupling and a few other things. And there's a standard dynamics. As you burn it for longer and longer, it grows, then eventually gets balanced off by relaxation. And this decay here is due to the photosensitizer burnout. So radical species are highly reactive. They react with various impurities in the sample. They react with the walls. And so less and less photosensitizer is available for that cyclic reaction to occur. And so eventually you just burn out the entire sample. And the reaction stops. Interestingly, if you just shake it, oxygen tends to reoxidize the photosensitizer and you get your intensity there. Alternatively, one can get hydrogen peroxide, but it tends to be frowned upon in biological community.
So you can spin the sample while burning?
No, because of the rigid geometry of the light delivery. It's the coaxial insert. In principle, you could probably get it to spin.
And that could give you a better result in this.
We never tried. The rigid character of that geometry meant that you simply put a few twists on your optical fiber and it will snap out of the system. One can certainly spin with the light delivery from the top with a pulsed laser, but again, magnet is drifting here and there because of the fluctuations in air pressure, and drawing spinning air would disrupt the balance of the air pressure. And so again, in practice, we never do. Applications, well, green fluorescent protein, we've labeled it with 19F because we couldn't get any signal on the protons, the sensitivity was too low. And there are various tyrosines in there which have been labeled with fluorotyrosine instead. You can actually persuade bacteria to incorporate fluorotyrosine instead of natural tyrosine into a protein before they die, which they very quickly do. And then, well, the things which are on the surface give a signal, things which aren't on the surface don't give a signal, and you can then establish which residue is on the surface. There are various unfolded states. You can unfold it with guanidinium chloride, you can unfold it with urea, you can unfold it with pH, and then there are various broad signals in various phases that, after pretty complicated analysis, can actually give information about how the protein folds. So there's GFP, it's a barrel, and there is a fluorescent group in the middle of it. So only solvent-accessible residues get polarized. Typical enhancements in real-life situation this was, with a colored protein which absorbed strongly at the laser wavelengths, about 10 to 15-fold compared to Boltzmann level. Can sustain it for several seconds, and importantly, you get your sample back. It doesn't get hydrogenated or anything as a result. You can just re-purify it, and then it's the same protein again. So, for example, if we mutate this residue away, the signal disappears. That is the NMR spectrum, that's the CIDNP spectrum, so you can see this, say, got polarized with negative signs, which is probably on the surface, whereas this thing didn't, probably isn't on the surface, and so on and so forth. So see, this doesn't get polarized, whereas these things do get polarized. And so some structural information at great pain and labor can be extracted out of those spectra. That's a result of some relaxation analysis. We've mapped the order parameters from relaxation theory. We mapped the accessibility of the highest occupied molecular orbital, which is where the electron is being taken away by the electron transfer with quantum chemistry. Then mapped the solvent accessibility, and this blue is the extent of the CIDNP effect that you see on that thing. So something which are highly ordered in the protein core and not accessible aren't polarized, but things which are on the surface and as a result considerably floppier, so with low order parameters, do get polarized and can be detected. Alright, so applications are all very well, but before you make those applications, you need to write software. And particularly with a pulsed laser, because 2 extra timelines are added on top of the array and the gradient, programming does tend to become complicated. So there's the laser lamp, which we need to flash to invert the populations in the lazy medium. Then there's the Q switch with its own latency and switching time. Then there is a pre-suppression because you want to get rid of the pre-existing magnetization in there. And then there's a basically detection pulse and the actual detection. And with microsecond time-resolved laser, because this pulse is also microsecond, what you flip into the transverse plane has microsecond time resolution. So after you flipped it, of course, you can detect it for a second, but the actual flipping time is about a microsecond, and so you can actually, by shifting this tau time, capture microsecond scale radical dynamics in the system. And that was done, but it took a bit of synchronizing, so those 2 extra TTLs and the various latencies involved had to be mapped and programmed around, particularly seeing as variant spectrometers have got this ROF1 and ROF2, which are not directly user editable, and so we had to go into the headers. Thankfully, variant programming language is C, and they supply the actual headers, so I had to go into the header, and when variant has its ROF1, after the pulse, the gating delay, I think it is called, I had to stick the laser control statement before the gating delay in the variant header, rather than the actual pulse sequence that was going ahead. So it is a bit of tweaking on the programming side there as well. So this 100 millijoules at 355 10 nanoseconds various technical parameters of these things. What you can also do is something that actually came up in conversations with Malcolm a few months ago. If you have a reservoir of negative temperature, you can repeatedly bring your system in contact with it and get the population higher and higher and higher and higher in the system. And we can, of course, do repeated laser flashes in there and store the magnetization in between somewhere. And so we can just destroy all magnetization with a crash pulse and then just run the lamp and the Q switch in a loop. Then, as soon as we've generated some longitudinal polarization, put it in the transverse plane, evolve it there until the next laser cycle. Laser pulses every 100 milliseconds. So we need to keep it going somewhere and keep refocusing it for 100 milliseconds. Then when the laser has reset itself and is ready to pulse again, we bring the magnetization back on the z-axis. Next laser flash pumps it even higher. And so there's a linear increase in the magnetization, at least initially, before it balances off by the various imperfections here, from the number of the laser flashes. Again, this is a highly favorable situation of just a single signal, not coupled to anything, in an extremely photostable molecule called DAPCO, which is really unique because it can survive thousands of laser flashes without photodegradation. Beware that the practical performance of such things on real-life molecules is likely to be considerably less beautiful than this. So this is one of the best cases. So yeah, we can perform intermediate storage and then accumulate multiple flashes to get magnetization higher and higher and higher. Well, what can you do with it? You can measure these hyperfine coupling constants. You can fit the microsecond scale magnetization kinetics. So that's the kinetics of the longitudinal magnetization, which has been flipped into the transverse plane and thereby frozen for later detection. Study various relaxation processes, that's the temperature curve in glycerol. CIDNP changes sign. This is a signature of viscosity dependence, is a signature of dipolar type cross-relaxation processes, but those were hyperfine cross-relaxation in intermediate radicals, something that's extremely difficult to actually measure experimentally. So various interesting things can be determined and see the literature. What else can be done with CIDNP? The polarization levels, again, are not actually huge, certainly not on the scale of things that you get from the DNP effect. We actually managed to find a relaxation mechanism for CIDNP, which was based on G hyperfine cross-correlation. Most of you know what DD-CSA cross-correlation is. It's a result of the geometric lock between dipolar and CSA interactions as the molecule tumbles. There exists a similar cross-correlation between the G tensor and the hyperfine tensor in a rigid molecule as it tumbles, and then G hyperfine makes the electron singlet or triplet and cross-correlates it to a singlet, which is conditional upon the nuclear spin state, which is similar to that chemical sorting. So we actually found, as Jud's referee pointed out, rather benevolently, a relaxation mechanism for CIDNP in at least some systems in rigid radicals, only in the cases when the hyperfine anisotropy is huge, particularly on 19F. Well, that's all there is to be said about my experiences with cidmp. Lots of thanks in particular to Peter Ho, who really masterminded the whole project. It was in his labs that I was doing it. To Chris Stimmel, Stefana and Peter, we did some photosynthetic reaction systems work. GFP was provided by Tim Krebs and Sophie Jackson. My group, in the Durham days when some of that was published, and these fine organizations for the funding, that's Durham Cathedral. Right, questions? In principle, we can build a cidmp machine here on a laser pointer and a fiber in a couple of hours, but whether it's going to be useful for anything is an open question.
So this is like an optical pumping, you say?
So you need a laser. Those days, they were really expensive. So getting a 5-watt laser was £20,000. In these days, 5-watt laser is 5 laser pointers from eBay. Yeah, they actually sell 2-watt laser pointers.
Highly coherent.
We don't need coherent light.
Totally coherent.
It just needs to be there for excitation. You know, a sufficiently strong lamp would do, but lasers tend to be more convenient.
And
How about UV lights?
You can use UV, it's just absorbed by other things than the photosensitizer. You'd have your protein, and every aromatic residue would absorb in the ultraviolet, whereas the photosensitizer actually absorbs in blue-green. Most proteins are transparent in blue-green, so blue-green light is preferred.
So you're using the pulsed field laser, right? Pulse laser.
We use both. Pulsed one
Can
is
you-
much harder to work with, but a bit more informative on the kinetics side. Okay. Want to experiment with that, give me a shout.